Hi, Mr. Calix here from Math Magicians. We'll continue with our Precalculus course. Today we're going to see functions and their properties, third video. The first exercise says, determine whether the function is bounded above, bounded below, or bounded on its domain. Bounded above means that it will have a maximum value. Bounded below indicates that it will have a minimum value. And bounded is that it's bounded above and below already. We have our first equation. It says y is equal to 2 to the x. As you know, if you substitute any number in x, it will always give you a positive answer because what you do when you put a negative number, it becomes a fraction. Okay, so if we know that the domain is all real numbers for this equation, we can use any number that we want to. So we're going to use these 5 numbers. If we substitute this negative 2 into the x, we will have as an answer 0.25 because it's 1/4. If I substitute negative 1, it will be 1/2, that is 0.5. If I substitute 0, every number with a 0 power is always going to be 1. If we substitute 1, it's going to be 2. If we substitute 2, it will be 4. With this, we're going to make our graph. It says to make the graph from negative 2, let's say that this is 1 and this is negative 2, to 0.25 will be here. Negative 1 with 0.5, 0 with 1, 1 with 2, and 2 with 4. As you can see, your graph moves this way. Your graph moves this way. Now, once you have that your graph moves this way, as you can see, you will never intersect this line. That means that it's going to be bounded below. Or we know it that because every number that I substitute here will always be positive, that indicating that it will never be under the 0. Okay, now let's make the next exercise. The next exercise, as you see, it has a square root. So for this exercise, we have a restriction. It has to be positive or a 0, the answer. That means that 1 minus x to the square has to be greater or equal to 0. If we solve for x, in this case, we send the 1 to the other side, it becomes a negative number. We will have, that is, negative x to the square is greater or equal to negative 1. Then this negative sign indicates that changes the inequality. So you're going to have, that is, x to the square is less or equal now to negative 1 over negative 1. If you solve this, is x to the square is less or equal to 1. But since we know that when we send a square power to the other side, it becomes a square with positive and negative, and you have to change the symbol for the negative again because you're changing for both, this will actually be x is less or equal than 1 and x is greater or equal than negative 1, because remember that when you send the square to the other side, it becomes a square root of positive and negative. Once we have this, we have a domain. Okay, I know that my answers are between negative 1 and 1 because it says that it has to be greater than negative 1 but less than 1. It has to be somewhere in between using those numbers. If we use a table of values, for x and y table of values, the only numbers that we can use are numbers that are between those numbers, negative 1 and 1, with those numbers. If I substitute negative 1 here, my answer would be 0. If I substitute 0 here, the answer is 1. If I substitute 1 again, the answer is 0 again. Once we have this information, we make our graph. It says negative 1 with 0, 0 with 1, and 1 with 0. As you can see, your graph does not continue moving upward and does not continue moving downward. That means that this graph would be bounded above and below. We just say that it's bounded. Let's make the next exercise. It says, use a grapher to find the local maxima and minima and the values of x where they occur. Give values rounded to 2 decimal places. As you can see, I use the tool here, a grapher, to find my graph. And you do not have maxima because the graphs continue forever moving on top, indicating that you can use any number that is greater than, in this case, 11. But it does have a minima value here. The minimum value, you find it by pointing your grapher, and it says that your minimum value is exactly at 0.5, 3.75. So we say that we have a local minima. It's set to round to 2 sig figs. So it will be in x at 0.50, and in y would be, let's use a comma, in y would be at 3.75. You can write it this way, or you can say that x is equal to 0.50. and y is equal to 3.75. Any of the 2 ways is correct. Let's continue. Now we're going to talk about symmetry. Okay, it says for all x in the domain, if the function, or if you substitute a negative sign inside the x, and it gives you the same answer as the function, is called an even function. The examples look like these graphs. Okay, the graphs look the same in both sides, okay, in both sides of the x. Then you have the numerical part. The numerical part indicates that when you substitute the values of x that you choose, they will have the same numbers. Okay, they will have the same numbers as answers. Then you have the algebraic form of odd functions. Okay, an odd function is that when you substitute a negative inside the x, but it gives you that the function is completely negative, it's equal to each other, is called an odd function. The graphical form would look like this. It looks very similar when it's moving up as when it's moving down. And the numerical part, they have the same number, but with different signs. For example, you have here negative 27 and 27. Let's make the next exercise. He says, state whether the function is even, odd, or neither. Support graphically and confirm algebraically. Okay, so we're going to support it graphically and then we're going to confirm it. Now for this, we're going to use a table of values to make the graph. As you can see, you can substitute any number you want to here because your domain is all real numbers. Any number that I substitute here will give me an answer. It will never be negative, indicating that it will be all real numbers. If I can use any number, I'm going to use this set. And what we do is that we substitute. If I substitute, for example, negative 2, in this 2 is the square root of 6, and the square root of 6, once you round it and find it, it will be 2.5. If you substitute negative 1, it will tell you that it's 1.7. If you substitute 0, it will be 1.4. Everything is rounded here. If you substitute 1, again, it's 1.7. And if you substitute 2, it has to be 2.5. As you can see from here, we can say that it's even. We can say already numerically that it's even. Now we're going to support it graphically. So we're going to make our graph. It says graph negative 2 with 2.5. It would be around here. Then we have negative 1 with 1.7, 0 with 1.4, 1 with 1.7, and 2 with 2.5. Okay, as you can see, your graph supports the answer. Okay, it looks even. Okay, we can say that it's even for sure, but it says to confirm algebraically. The confirmation for even is this one here. Okay, we're going to make that confirmation. Okay, so we are going to substitute a negative inside every x that we have of the function. And if it gives us the same function, then we are going to say that it's even. So if I substitute the negative in every x and I evaluate that negative to the square power, I actually have the same function, indicating that f to the negative x is equal to f to the x. If they are equal to each other, that means that it's even. So we demonstrate, we found it numerically, we support it graphically, and we demonstrate it algebraically. Let's continue now with asymptotes. The line y is equal to b is a horizontal asymptote of the graph of the function of y is equal to a function. If that function approaches the limit of the horizontal asymptote, or the y equals b, as x approaches to the positive or negative infinite. Okay, you have some limits that you can write using here. It says, for example, that the limit of x when it approaches to or from the infinite from the left of the function is equal to b. And the limit of the function when x approaches this infinite, but from the positive side, is also equal to b. That explains that one. Now this one says that when x is equal to a is a vertical asymptote of the graph of the function y is equal to a function if the function approaches a limit at positive or negative infinites as x approaches from either directions. So for this one, we have another type of limit. This is an or here. The limit of x when it approaches, the limit of the function of x when it approaches the vertical asymptote from the left is equal to positive or negative infinite. And we can say, or the limit of x when it approaches a, now from the positive side, is also equal, let's call this function, is also equal to the positive or negative infinite. That explains the limits. Let's make this exercise. It says, use a method of your choice to find all horizontal or vertical asymptotes of the function. Okay, so we're going to choose our own method. We have 3 minus x here. With this 3 minus x, with your denominator of a rational function, you can find your vertical asymptote. Because 3 minus x has a restriction, it cannot be equal to 0. So if I solve for x here, I have that negative x cannot be equal to negative 3. If you send that negative to the other side, remember that it moves as a division, you will have that x cannot be equal to 3. This here, x equals to 3, would be your vertical asymptote. Okay, so we found the vertical asymptote already. The horizontal asymptote, you have some rules. For example, it says that if the degree of the numerator is greater than the degree of the denominator, then you do not have any asymptote. There is no horizontal asymptote. Okay, HA is horizontal asymptote, VA vertical asymptote. And the asymptote that you get here will be a slant asymptote. When n is less than m, then your horizontal asymptote would be when y is equal to 0. And when n is equal to m, what you do is that you divide both your leading coefficients of the degrees. And this would be your horizontal asymptote. Okay, this is this case here. As you can see, n is equal to m. The degree here is equal to a degree here. So to find my horizontal asymptote, I am just going to make the division of the two leading coefficients. Y is equal to, the leading coefficient here is 1, and the leading coefficient on the denominator is negative 1. Y is equal to negative 1. We found them both. Okay, this would be your horizontal asymptote. With that, we're going to make our graph. Okay, for our graph, we're going to use our table of values. And I recommend use, let's say 3 numbers before, 3 numbers after, of what? Of the restriction. So we know that 3 is an asymptote. We're not going to use it. We're just going to use 3 numbers that are before and 3 numbers that are after. For example, before we can say that we can use 2, 1, and 0. And after 4, 5, and 6. Okay, indicating that 3 in the middle is the asymptote. If we substitute this information, we'll have the 0 is 0.7 once rounded. If we substitute 1 is 1.5. If we substitute 2 is 4. If we substitute 4 is negative 6. If we substitute 5 is negative 3.5, and 6 would be negative 2.7. So let's make our graph here. I cannot intersect in 3 in x, so 1, 2, 3. I cannot intersect this line because it's an asymptote, 3 here. And we cannot intersect the negative 1 also. So let's use negative 1 here, and let's make our line there. Okay, so those 2 lines cannot be intersect because they are asymptotes. Now let's start graphing. It says 0 with 0.7. If 1 is here, 0.7 is around here. 1 with 1.5, it's in between 1 and 2. 2 with 4, let's call it here. As you can see, your graph has a curve this way. Okay, it will never intersect this line here. Let's make this one a little bit longer so you can see that it will never intersect. So we are okay with the asymptote so far. Now let's make the other one. Let's move this here. It says 4 with negative 6. So 4 is here. This is negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. It'll be around here. Then we have 5 with 3.5. And this is 1, 2, 3. It would be in the middle here. And let's make this line a little bit longer. Let me see. Okay, there we go. And then we have 6 with 2.7. As you can see, you're coming back up, right? Okay, so if we make our graph here again, you will see that you have your curve. So that demonstrates that the asymptotes were correct. Thank you for watching. And don't forget, math is magic.